Welcome back to our channel. Today's problem mixes inverse trigonometric functions, chain rule, and logarithmic differentiations. So in this question, we'll differentiate the function y equal to the ln of sec inverse of 3x. I'll go slowly and show every algebraic step. This is exactly the kind of problem that appears on higher level exams. So let's start. The first thing we identify is that this question is a function of another function, with our internal function being all of this and our external function being ln. So anytime recalling back on the different rules of trigonometry, anytime we have a function which is a function of another function, there is one rule which comes to our mind. What rule is it? It is the chain rule. And what does the chain rule state? The chain rule states the derivative with respect to x of a function f of g of x is equal to f prime of g of x times g prime of x. So the first thing is we need to first of all identify our g of x and then our f of x. So our g of x is our inner function, so we'll say let g of x be equal to sec inverse of 3x. Now let f of u be equal to ln u. This implies that f prime of u, which is equal to the derivative with respect to x of ln of u, with respect to u, with respect to u of ln of u is equal to 1 on u. What do we do then? U equal to g of x implies that f prime of u, which is equal to f prime of g of x, is going to be equal to 1 on g of x, which is equal to 1 on sec inverse of 3x. Now let's calculate g prime of x. G of x is equal to sec inverse of 3x, and if you notice, g of x is still a function of another function, with our internal function being 3x and our external function being sec inverse. So what's the first thing we do? We will say let's call our internal function v. Let v be equal to 3x. What do we do then? Let our external function u, is our external function, u of, let's say u of, let's not use v and u, let's use two different functions. Let's use h of x here. Let's use h of x for internal function. Let h of x be equal to 3x. Now g of u is equal to sec inverse of u, implies that g prime of u is equal to derivative with respect to u of sec inverse of u, which, from recalling from the previous video on the derivative of the inverse trigonometric function sec x, this gives us 1 on absolute value of u square root of u squared minus 1. So u equals to h of x implies that g prime of h of x is equal to 1 on, what's our h of x? Absolute value of 3x square root of 9, or let's put in bracket 3x. Let me erase this and write it clearly. 3x squared minus 1, which gives us 1 on absolute value of 3x square root of 9x squared minus 1. H prime of x then is equal to derivative with respect to x of 3x, which gives us 3. So this then implies that g this implies that g prime of x, which is equal to g prime of h of x times h prime of x, is equal to what's g prime of h of x, 1 on absolute value of 3x square root of 9x squared minus 1 times h prime of x, which is 3, leaving us with 3 on absolute value of 3x square root of 9x squared minus 1. So we can then conclude all what we need to do now is substitute our first function g prime of x and our second function f of this, which we have calculated here. This is it here, f prime of g of x. So we all what we need to do is just multiply both functions to come out with the derivative of our complete function. So the derivative with respect to x then of our function f of x is equal to, we have f prime of g of x times g prime of x, which gives us what is f prime of g of x. F prime of g of x is the function 1 on sec inverse of 3x, 1 on sec inverse of 3x times what is g prime of x. G prime of x is the function 3 on absolute value of 3x square root of 9x squared minus 1. Simplifying this or trying to make it look much more better, we have 3x root 9x squared minus 1 sec inverse of 3x. So what we need to do then is simplify this solution. We have 3 divided by, this 3 can come out of the absolute value, leaving us with 3 absolute value of x square root of 9x squared minus 1 sec inverse of 3x. 3 cancels 3, leaving us with 1 on absolute value of x square root of 9x squared minus 1 sec inverse of 3x. So we can then conclude, therefore, the derivative with respect to x of our function f of x, which is dy on dx, is equal to the function 1 on absolute value of x square root of 9x squared minus 1 sec inverse of 3x. We box our answers. Now, after calculating this, we need to define the domain conditions for which this our derivative is valid. If you notice, this absolute value was present here because of the domain condition which sec x imposes in our calculations. So in this our case, sec inverse of 3x still imposes a domain condition, and these domain conditions can be calculated. Let's write domain conditions. We start one. Arc sec of 3x defined, or it's valid for absolute value of 3x greater than or equals to 1, which implies that absolute value of x is greater than or equal to 1/3. Now, ln of arc sec 3x is defined for sec inverse of 3x greater than 0. 3 arc or sec. Arc sec is the same thing as sec inverse of 3x equal to 0 when 3x equal to 1, implies that x equal to 1/3. But ln of 0 is undefined, which implies that exclude x equal to 1/3. So our final domain is absolute value of x greater than 1/3, but x not equal to 1/3. So what can we then conclude? Therefore, the derivative of dy on the x is equal to 1 on absolute value of x square root of 9x squared minus 1 into sec inverse 3x, comma, valid for absolute value of x greater than or equal to 1/3, but x not equal to 1/3. And this represents our final solution. So just to highlight common mistakes students usually make, the first one is most of the time they forget the absolute value in arcsec derivative. That is, they put the x without putting the absolute value. The next is they forget to multiply by inner derivative. That is d on the x of 3x. Like in this case, we have sec inverse of 3x, and in order to calculate this, it is the derivative of sec inverse of u times the inner derivative of the inner function 3x. Most of the time, students forget to differentiate this inner derivative and multiply it. So those are just a few of the common mistakes students mostly make. So thank you for taking part in this video. We'll see you in the next video where we're going to tackle a much more complicated question than this. So till then, bye. In today's lesson, we'll tackle challenging differentiation problem that combines a product rule, chain rule, and inverse tangent differentiation. So first of all, what is our function? Our function is given by y equal to x squared times tan inverse of 1 on x. So let's start with the differentiation. Before we always start with the question, we first of all observe the question. How does this question look like? What are the different identities we observe in this question? For example, take this question. The first thing we observe is that this question is a product of two different functions, with our first function being x squared and our second function being the tan inverse of 1 on x function. Knowing already that our function can be represented as a product of two different functions, this already hints to us that what we need to apply here is the product rule. Now, before applying the product rule, we need to recall the product rule. So what does the product rule state? The product rule states that the derivative with respect to x of the product of two functions uv is equal to u dv plus v du. So first of all, what is our u? What is our v? We will let u be equal to x squared. This then implies that du on the x, which is equal to u prime, is equal to d on the x of x squared, which is equal to 2x to the 2 minus 1, which is equal to 2x. Now let's move on to our v. Let v be equal to tan inverse of 1 on x. What was the first thing we noticed about this? We noticed that v is a function of another function. That tells us that in order to calculate v prime, we need to apply the chain rule. So what does this chain rule tells us? Recalling, the chain rule tells us that the derivative with respect to x of a function f of g of x is equal to f prime of g of x times g prime of x. So first of all, what is our f prime? Our f of x. Our f of x is the external function tan inverse, and the inner function g of x is 1 on x. So we'll say let f of u be equal to tan inverse of u. This then implies that f prime of u is equal to what's the differential of tan inverse, recalling from the previous video on the derivative of inverse trigonometric functions, it was well proven and well stated that the derivative of the tan inverse of u with respect to u gives us the function 1 on u squared plus 1. So what do we do then? U equals to g of u equals to 1. Let's first of all identify our g of x. Let then g of x be the function 1 on x. This implies that, which is the same thing as x to the negative 1. This implies that g prime of x gives us negative 1 x to the negative 1 minus 1, which gives us negative x to the minus 2. So u equal to g of x implies that f prime of u is equal to f prime of g of x, which gives us the function, implying that f prime of g of x gives us the function was f prime of u 1 plus what's our g of x, 1 on x squared plus 1. Simplifying this, we have 1 on x squared plus 1. Simplifying this further, what do we have? We have 1 on x squared plus x squared on x squared, which gives us the function x squared on 1 plus x squared. So now we have our term f prime of g. We also have g prime of f of x. We can then say the calculation of f of g of x is possible. So let's move on to this. How do we then calculate? So this f, yes, it is, yes, the calculation of v prime is possible. Yes, this derivative here is the same thing as the derivative of v prime. So this implies that v prime, which is the derivative with respect to x of f of g of x, gives us the function this times this. What is this? This is what we have calculated here, and this is our g of x. So it gives us, let's start with g prime of x, 2 into x squared on 1 plus x squared, which gives us negative 1 on 1 plus x squared, as x to the negative 2 cancels with x to the 2. Yes, negative 2. Yes, x to the 2. And these two terms cancel each other out, leaving us with negative 1 all over 1 plus x squared. So we now have our v prime, we have our u prime, we have our u, we have our v. We can then calculate d on the x of uv. So d on the x of uv is equal to u dv. What is our u first of all? Our u is the function x squared. So x squared. What is our dv? Our dv is the function we recently calculated, 1 plus x squared plus v du. So what is our v? Our v is the function tan inverse of 1 on x. Tan inverse of 1 on x times, that's v du. And what's our du? Our du is the function 2x. Simplifying this further, we have minus x squared on 1 plus x squared plus 2x tan inverse of 1 on x. So we can then conclude that therefore the derivative of our function y, or the y on the x, gives us the function negative x squared on 1 plus x squared plus 2x tan inverse of 1 on x. We encase or box our answer. So this is the derivative of the function y equal to x squared times tan inverse of 1 on x. In this equation, we use the product rule, chain rule, and inverse tangent derivatives all together. Problems like this show how rules combine in real scenarios. In the next video, we'll move on to another challenging problem with inverse trig functions inside fractions. So stay tuned. See you in the next video. Bye. So in this video, in this question, we'll tackle one of the hardest problems so far, which is y equal to e of x, e to the power x, times the cosec inverse of the function square root of x squared plus 1. This will test all the rules we have learned, product rules, chain rules, and the derivative of inverse trig functions. So let's dive in step by step. The first thing we are going to do is to recall certain rules or certain formulas which we are going to use during the solution of this question. The first one is the product rule. What does the product rule state? It states that the derivative of the product of two terms is u dv or u dv, that is u dv plus v du. It is the same thing. That is, you hold one and differentiate the other, plus you hold the other and differentiate the first one. Now, this is the chain rule, and what does the chain rule state? It states that the derivative with respect to x of any function f of g of x is equal to f prime of g of x times g prime of x. Now let's move on to the derivative of our inverse trig function, which is given by the derivative with respect to x of cosec inverse of u. Let's put x of let's use x or u, one of them. Let's just use u in this case. That's the general expression, is equal to negative 1 on absolute value of u square root of u squared minus 1 times u prime. This is just an application of chain rule, which, like, if we're having a function like this cos u, all of this formula here is just an application of chain rule on the general expression. Yes, so that's the formula. We are going to apply it to solve these questions. So the first thing, when we look at this question, we notice that this question is a function multiplied by another function, with our first function being e of x and our second function being all of this. This already hints to us that in order to solve this, we need to use the product rule. In the product rule, we have two functions, u and v. So what is our u? What is our v? That's our first step. We identify our u and v. So first, let u be the function e of x. This implies that u prime is e of x, since the derivative of e of x with respect to x still gives us e of x. Now let's move on to v. Let v be the function cosec inverse of square root of x squared plus 1. Right? The first thing we notice that this is a function of another function. And what does the derivative function of another function tells us? It tells us that v prime is going to be equal to the derivative with respect to x of the function cosec inverse of u, derivative with respect to u, sorry, with respect to u of this function, times derivative with respect to x of the function of the inner function square root of x squared plus 1. So let's start with this. All of this gives us the term derivative of cosec u gives us negative 1 on, we have absolute value of u here, square root of u squared minus 1. U prime here is the derivative with respect to u of u, which gives us 1. So all of this can be cancelled out and replaced directly by 1. Now let's move on to our second term. This is the same thing as, what's the first thing we are going to do? We notice that this is the function, is still a function of another function, which is a derivative with respect to x of x squared plus 1, all that to the power half. So let's just apply the chain rule directly rather than letting. This gives us the derivative with respect to u of the function u to the power half times the derivative with respect to x of our inner function x squared plus 1. This simplifies to derivative of u, we have half u to the power negative half times derivative of that, we have 2x. But what is our u in this case? Our u in this case is this function. So this gives us half into x squared plus 1 negative half times 2x, leaving us with x into x squared plus 1 into negative half. So this then implies that our v prime is equal to our first term here, where u here is this inner function square root of everything. That is our u. Our u in this case is the square root of the whole of that function. So we have negative 1 on absolute value of square root of x squared plus 1 into we have square root of u squared minus 1 square root of u squared, that is x squared plus 1 all that squared minus 1. Yes, that's our v prime. Is our first term is our v prime is yes, it's all of this times all of this being what I've just written, all of this then gives us this. So this times x into x squared plus 1 all that to the power negative half. Simplifying this, we have negative 1 all that on square root of x squared plus 1. There's no need for me to put the absolute value because absolute value converts negative to positive, whereas the square root of any number is always positive. So we can cancel it directly out and not consider it. All of this square gives us x squared plus 1 minus 1 times x into x squared plus 1 all that to the power negative half. This then simplifies to negative 1 on square root of x squared plus 1 into x squared 1 minus 1, it cancels out, square root of x squared gives us x times x into x squared plus 1 all that to the power negative half. X cancels x, leaving us with negative 1 x squared plus half to the power negative half divided by x squared plus 1 to the power half, which then simplifies to x squared plus 1 to the power negative half minus half, which then simplifies to negative 1 x squared plus 1 all that to the power negative 1, which can be written as negative 1 on x squared plus 1. So our v prime is done. Now let's move on to our general expression. In order to differentiate our general expression, we needed to calculate u and u prime. We need to determine v and calculate v prime, and we have done it. Now in order to we then need to put all of this into place, that's into our initial equation u prime v plus v prime u, in order to then calculate the derivative of our initial function, that is dy on dx. So this then implies that dy on dx is equal to u. What is our u? Our u is e of x dv plus v. What is our v? Our v is cosec inverse of square root of x squared plus 1. Cosec, there's no need for me to write it completely. Cosec inverse of square root of x squared plus 1 times, what's our du? Our du is still e of x. So the first thing we notice is that e of x is common in both terms, so we can factorize it out, leaving us with negative 1 on x squared plus 1 plus cosec inverse of square root of x squared plus 1. So what can we then conclude? Therefore, the derivative of y with respect to x is going to give us e of x negative 1 into x squared plus 1 plus cosec inverse of square root of x squared plus 1, and we enclose, or box our answer. So though this question might have looked a little bit complicated, the applications of or the way to solve it was just done by the applications of the same rules and methods which we have had to study, we have had to apply in previous examples. So differentiation in general is not that complicated so far as you master all the differentiation rules, the differentiation of basic identities like basic trig functions, basic logarithmic functions, basic exponential functions, and their general forms. The moment sorry the moment those are mastered, differentiation becomes easy. So that's it. A very advanced derivative combining exponential, product rule, and inverse cosecant. This is a great example of how all the differentiation tools come together. In the next video, we'll try a different type of heavy problem with implicit differentiation involving all the different functions we've had to study. So see you in the next video. Thank you and bye. Let's start the question. The aim of this question is to differentiate y, which is equal to x squared plus 3x, all that times sine x. So first of all, when we have such a question, what is the first remark we can make? The first thing we can identify is this question is made up of two different functions. That is, this first function and this second function, and these functions are multiplied by each other. What does that tell us? That tells us that y can be written as a product of two functions, where f of x, our first function, is x squared plus 3x, and g of x, our second function, is sine x. So perfect. So the first thing, after identifying that y can be written as a product of two different functions, we then need to reflect on what rule can we then use to differentiate this function. What rule is applicable to functions which can be written as a product of two other functions? From our memory, we recall well that it is the product rule. And what does the product rule state? The product rule states that if y is equal to f of x times g of x, then y prime is equal to f prime of x, g of x, plus f of x, g prime of x. So in this question, in this expression, we have four different terms. Out of these four different terms, two of them are already known, leaving us with f prime of x and g prime of x to determine. So that is where we should start right now. The first thing, f prime of x. First of all, we rewrite our f of x, which is equal to x squared plus 3x. Now f prime of x is the differential with respect to x of the function x squared plus 3x, which is equal to the differential with respect to x of x squared plus the differential with respect to x of 3x. This is from our sum rule. And this then is equal to 2x to the 2 minus 1 from power rule plus 3 differential with respect to x of x, that is the constant multiple rule, giving us 2x plus 3 times 1x to the 1 minus 1. This gives us 0. This gives us x to the power 0, which is equal to 1. So this leaves us with 2x plus 3 times 1, which gives us 2x plus 3. So I've gone through the first step of this question, finding f prime of x. This leaves us now with the second question, the second step. How do we determine g prime of x? First of all, what is g of x? G of x is the function sine x. This implies that g prime of x is then the derivative with respect to x of the function sine x. And if we recall well from the trigonometry, from the derivative of trigonometric functions, the derivative of sine x gives us the function cos x. So we can then say that we have all the four terms which we can use to come out with the derivative of our function. This leaves us one step, substituting each function into our final expression. So what does our final expression say? It states that y prime is equal to f prime of x. What is f prime of x? From our previous differentiation, f prime of x is the function 2x plus 3. That is 2x plus 3 times g of x. What is g of x? G of x is the function sine x. Plus, what is f of x? F of x is the function x squared plus 3x, x squared plus 3x times g prime of x, which is the function cos x. After having our general expression, we then need to simplify it to the simplest form. This leaves us with 2x sine x plus 3 sine x plus x squared cos x plus 3x cos x. Note that I am expanding these brackets in an attempt to simplify the question. So if upon expanding the brackets, I notice that these questions cannot be simplified more, then the simplest form is going to be this form which had the bracket. So let's identify, can this expression still be simplified? Question mark. The first thing we notice is this expression cannot be simplified. Why can't it be simplified? Because each and every of the terms are unlike terms. This leaves us with 2x plus 3 sine x plus x squared plus 3x cos x. And this can be written as, or this can be identified as the simplest form of our equation. This leaves us with one conclusion. Therefore, the derivative with respect to x of our function, which is x squared plus 3x sine x, x squared plus 3x sine x, is 2x plus 3 sine x plus x squared plus 3x cos x. We box our answers. So let's move on to our second question. What does our second question say? Differentiate the function y equal to e to the x on 1 plus cos of x. When we look at this question, just like the previous question, we identify a numerator and a denominator. What does that tell us? We are working with a fraction. Sorry, but we can, let's not say fraction, but we are working with a function which can be expressed as one function divided by another. So what's the first thing to do? We identify each function. So we'll say, let our f of x be equal to e of x, e to the x, and g of x be equal to 1 plus cos x. Knowing already that our function y can be written as one function divided by the other, or g of x divided by f of x, what rule do you think can be used in this case? Of course, there is only one rule. There are many other rules, but in this case, the simplest and fastest, or the easiest, to identify is the quotient rule. And what does the quotient rule state? It states that the derivative with respect to x of a function f of x on g of x is equal to bottom d top, that is g of x d top, f prime of x minus top d bottom, all over bottom square. So in this expression, we're having several terms which we need to calculate. Let's start with our first term, f prime of x. What is f prime of x? Is simply the derivative with respect to x of the function e of x. And if you can all remember from our video on the derivative or the derivative of exponential functions, it was well mentioned and well derived that the derivative with respect to x of the exponential function e to the power x remains itself. That is, it remains itself. It remains unchanged. So this gives us e to the x. So let's move on to our denominator. The derivative with respect to x of our denominator g prime of x, g of x, which is same as the derivative with respect to x of the function 1 plus cos x, is same thing as the derivative with respect to x of our function 1 plus the derivative with respect to x of our function cos x. Derivative with respect to x of our function 1 leaves us 0. Why? Because it was well said that the derivative of any constant gives us 0. So this leaves us with 0 plus, from our video on the derivative of trigonometric functions, it was well shown and well proved that the derivative of the function cos x gives us negative sine x. So this can then boil down to negative sine x. Our next function to calculate is the square root of our denominator, which is g of x squared. What is g of x? G of x is the function 1 plus cos x, and all this squared leaves us with leaves us to 1 plus 2 cos x plus cos squared x. We could expand it, or we could still leave it in this form, but for the continuation of this question, I'm going to use it in this compressed form, and if needed, I will then use the expanded version. So let's replace each term in our initial expression of our question, of our problem. So the derivative with respect to x then of our function y, which is equal to bottom g of x times f prime of x. What is g of x? G of x is the function 1 plus cos x times f prime of x, which is the function e of x, minus top, which is f of x, e of x, the bottom, which is 1 plus cos x, all that squared, all divided by the square. But sorry, I made an error. The derivative of the bottom is not this. I used the square of the bottom as the derivative of the bottom, which is 4. And what is the derivative of our bottom? Minus sine x, all that now divided by the square of our bottom. This leaves us with the expression e of x. We can factorize e of x on both sides on the two equations, since it's common on both sides, leaving us 1 plus cos x minus plus sine x, all divided by 1 plus cos x squared. So what can we then conclude? Our conclusion can then be written as the derivative, that is the derivative with respect to x of our function, what was our function again, sorry, e of x on 1 plus cos x, e to the x on 1 plus cos x is e to the x 1 plus cos x plus sine x divided by 1 plus cos x, all that squared. What do? We encase, or we box our answer. So thank you very much for following throughout this video. We are waiting for you guys on our next video, which is still going to be a question in this our problem solving series. Thank you. Bye. So let's start with question 1. Example 1. Example 3, sorry. What does example 3 states? He asks us to find y prime given y is equal to ln of the sine of x squared. So this is pretty simple, it's not a complicated question. So we're going to start. What is the first thing we identify in this question? We identify that this is an inner function. So what do we first say? We say let g of x be equal to this inner function sine x squared. This implies that y is equal to the ln of g of x. Recalling our the formula, the general formula which we had proven on the derivative of logarithmic functions of this form. It was well written that the derivative of such a function is g prime of x on g of x. So what is the first thing we need to do? Find g prime of x. So g of x is equal to the function sine of x squared. So we are going to let, what can we identify in this case? This is still a function of a function with our first function or our inner function being x squared and our outer function being the sine function. So the first thing we do is let a variable be our inner function x squared, implying now that our outer function g of x is the function sine u. Now g prime of x is g prime of u, our outer function g of u. Here's g of u. G prime of u is equal to the derivative of sine u is cos u. Our next thing to do is derivative of our inside function of u with respect to x is equal to the derivative with respect to x of x squared, which gives us 2x. Now the derivative with respect to x of g of x is same thing as the derivative with respect to u of g of u times the derivative of u with respect to x. This leaves us with, this is same thing as g prime of u times u prime. Is the same formula which we have always used when we work with the chain rule. I'm just writing that now with the same formula. This gives us cos u times 2x, which gives us 2x cos u. But what is u? U is x squared, leaving us with 2x cos of x squared. So having done this, all what we need to do right now is to replace this value in our initial function g prime of x divided by g of x. This leaves us with the derivative of y with respect to x, which is g prime of x on g of x, gives us 2x cos of x squared divided by our initial function, which is sine of x squared. We can then conclude that the derivative with respect to x of the function ln of sine of x squared gives us, sorry, I put 3 brackets here instead of 2. Yes, 3 is okay, 3 is needed, is the function 2x cos x squared divided by sine x squared. We encase our answers. So moving on to our second question, our second practice question. What did it state? Practice, or I mentioned example, but I can see use practice question 4. What does this question ask us to do? This question asks us to find y prime given y is equal to e to the x squared cos x. So friends, what is the first thing you can all identify in this case? This can still be written as the product of a product, a function which is the product of two functions, our first function being e to the x squared and our second function being cos x. So the first thing we're going to do is let f of x be our first function and let g of x be our second function. let f of x be our first function e to the x squared and g of x be our second function cos x. And what do we remember when we have such equation which concerns the multiple of two different functions? We use product rule. And what does product rule state? Product rule states that the derivative with respect to x of f of x times g of x is equal to f prime times g plus g prime times f. So all what we need to do is find f prime and g prime. So let's start. Let's start with g prime since it's much more easy. G prime of x, which is the derivative with respect to x of g of x, which is our function cos x, is the function negative sine x, and that is all. Let's move on to f prime then. F of x, first of all, is the function e to the x squared. We still notice that this is a function inside another function. That is a function of a function, not more a product of two functions, but a function of a function, with our inner function being x squared and our outer function being e to the power. So what do? We say let h of x be equal to x squared. This implies that f of x is equal to e to the h of x. Then the derivative with respect to x of every function e to the h of x, we can still recall from our derivative of exponential functions. We explained this formula, and this led us to h prime of x e to the h of x. So we need to find h prime of x. So let's start with, first of all, what is f of x? What is h of x? H of x is the function x squared. What then is h prime of x? H prime of x is the function 2x to the power 2 minus 1, leaving us with 2x to the power 1, leaving us with 2x. So what can we then conclude? The derivative with respect to x of our function e to the h of x, which is same thing as the derivative with respect to x of our function of f of x, which is same thing as f prime of x, is the function 2x times e to the, what's h of x? H of x is x squared. And from here on, all what we need to do is to substitute these different values, this our f prime of x, and this and f of x and g of x, all that into this equation. So what do we have? The derivative with respect to x then of f of e to the x squared times cos x is then equal to, what is f prime? F prime is the function 2x e x squared. What is g? Sorry, g is the function cos x plus, what is f? F is the function e to the x squared times, what is g prime? G prime is the function negative sine x. Now all what is left is for us to simplify these terms. This leaves us with 2x e to the x squared cos x minus e to the x squared sine x. Noticing that e to the x squared is common on both terms, we can factorize e to the x squared out of this expression, leaving us with e to the x squared of 2x cos x minus sine x. So what can we then conclude? Therefore, the derivative with respect to x of the function e to the x squared cos x is equal to e to the x squared 2x cos x minus sine x, and we end case or box our answer. Thank you very much for following us throughout this video. We hope to see you guys in the next video, where we're going to tackle the same problem solving series with 1, but this time on questions 5 and question 6, which are much more complex questions than the 3 and 4 we just solved. Thank you. See you guys. Bye. Today we're working on question 5. This one is interesting because it combines the quotient rule, product rule, and chain rule all in one function. So let's dive in. So what does this problem state? In this question, we are asked to differentiate this function with respect to x. First of all, notice it is a fraction. And what does this tell us? This means quotient rule will be needed. But if you look clearly at the numerator in itself is a product of two different functions. So what does this tell us? The product rule will also appear. So we're going to layer our differentiation rules carefully. So let's start. First of all, for my first observation, this question is a fraction, which tells us that the quotient rule is going to be needed. Recalling our quotient rule, our first step was to identify our numerator function and our denominator function. So what are we first going to say? We'll call our numerator function f of x. That is, let f of x be equal to our numerator function x squared plus 3 sine of x. And we're going to call our denominator function g of x. Let g of x be the function e to the x. Recalling our quotient rule, it states that the derivative with respect to x of any function of the form f of x on g of x is bottom d top minus top d bottom all over bottom squared. So in this question, or in this expression, there are three different terms we need to find. Our first term is the product g of x and f prime of x. Our second term is the product f of x and g prime of x. And our third term is the square root of g of x. So let's start with our first product. In this our first product, we already know our first term g of x. The remaining term is f prime of x. So let's find f prime of x. First of all, we call f of x. F of x is the function x squared plus 3 times sine of x. If we notice this function, we notice that this function can still be represented as a product of two functions. That is, we can say let the function u be equal to x squared plus 3 and v be equal to sine of x. Now we notice that f of x can still be represented as uv, which is the product of two functions, and this implies that the differential with respect to x of f of x, which is the differential with respect to x of our product uv, is equal to u dv plus v du, right? So in this term, still in this expression, we have two terms here, u dv and v du. But in our first term u dv, we don't yet know dv, and in our second term v du, we don't yet know du, which is same thing as u prime. So let's first of all find those terms. U prime is equal to the derivative with respect to x of u, which is the derivative with respect to x of x squared plus 3, and this gives us the derivative with respect to x of x squared plus the derivative with respect to x of 3. This is the application of our sum rule, which tells us that the differential of a sum is same thing as a sum of their differentials. So let's move on to this. Recall, what method can we apply to differentiate x squared? The method we can apply is the power rule. So derivative with respect to x of x squared is same thing as 2x to the power 2 minus 1, which gives us 2x. Let's move on to the next term. Derivative with respect to x of 3 It gives us 1. Why does it give us 1? Because 3 is a constant. And recalling our constant rule, it states that the derivative with respect to x of any constant is 0. Is 0. Sorry, Jesus. I wrote 1. Is 0. Is 0. Yes. So the derivative of any constant is 0. So let's move on. Replacing these terms in our initial expression here, we have the derivative with respect to x of uv is going to give us u. What is u? X squared plus 3 dv. What is dv? Dv is I've not calculated it. Oh guys, sorry. V prime, which is the derivative with respect to x of our term v, which is the derivative with respect to x, and what's our v? Sine x, gives us, if we recall very well from when we were working on trigonometric functions, it was well stated that the derivative with respect to x of the trigonometric function sine x gives us the function cos x. So we're just going to replace this here. What is dv? Cos x plus what is v? Sine x, and what is du? Du is this plus this, which is 2x plus 0, 2x plus 0. So this gives us cos x into x squared plus 3 plus 2x sine x. So what can we then conclude? Therefore, the derivative with respect to x of our function f of x, which is the derivative with respect to x of uv, which is f prime of x, is equal to the function x squared plus 3 cos of x plus 2x sine of x. So we have found our f prime. Now let's move on to g prime of x. First of all, we need to recall our g of x, and our g of x is the function e of x. So this tells us that the derivative with respect to x of our g of x, which is same thing as g prime of x, which is the derivative with respect to x of our e of x, is, now we then need to recall the derivative of exponential functions, and it was well stated that the derivative of the function e of x is e of x. That means it remains unchanged. So this gives us e of x. This concept or this response was well proven when we were working on the derivative or the differentiation of exponential functions. So in order, if you don't understand this derivative, you can quickly review the video on the derivative of exponential functions and come back to this video. So let's continue. This implies that our g prime of x gives us e of x. So now we have our g prime of x, we have g of x, we have our f prime of x, we have f of x. So what do? We replace in this formula. Sorry, we don't yet have g squared. Let's calculate it first. Now g of x, all that squared, gives us e of x squared, which gives us e to the 2x. So now that we have all the terms, we can simply replace it in the function. We notice that the derivative with respect to x of our function y is same thing as bottom d top minus top d bottom on bottom squared. Let's rewrite our functions. We notice that g of x is the function e of x, g prime of x is e to the x, g of x all that squared is the function e to the 2x, f of x is the function x squared plus 3 times sine of x, and f prime of x is the function x squared plus 3 of cos of x plus 2x of sine of x. x squared plus 3 of cos of x plus 2x of sine of x. So we can then substitute. This implies that the derivative with respect to x of our function y gives us g of x times f prime of x squared plus 3 cos x plus 2x sine x minus f of x squared plus 3 sine x times g of x e to the x, all that divided by e to the 2x. So what we can notice in these two terms is we have e of x common on both sides. So this gives us e to the x in bracket x squared plus 3 cos of x plus 2x sine of x minus x squared plus 3 sine of x, or divided by e2x, which is e of x times e of x. One e of x can cancel one of them, leaving us with, we then simplify this, we have x squared plus 3 into cos of x plus 2x sine x minus x squared plus 3 sine x, or divided by e of x. Now if we look closely to our numerator, we notice that there still exist two terms which are common, that is this term and this term, which have sine x in common. So we can factorize out sine x in both of these terms, leaving us with x squared plus 3 cos x plus sine x into 2x minus x squared minus 3. So this leaves us with, all divided by a of x, leaving us with x squared plus 3 cos x minus, we can still remove it out, x squared minus 2x plus 3 into sine of x, all divided by e to the x. So what do we observe? We observe that after replacing our terms and simplifying, we're able to obtain this function, which is the derivative with respect to x of our function y. So in conclusion, that is, therefore, the derivative with respect to x of our initial function x squared plus 3 sine x divided by e to the x gives us, which is same thing as dy on the x, gives us the function x squared plus 3 cos of x minus x squared minus 2x plus 3 into sine x, all divided by e to the x. We enclose or box our answers. So that's the derivative of our function. Notice how we combine quotient rule with product rule in the numerator, then simplify it carefully. This is exactly the kind of problem that strengthens your differentiation techniques. So in the next video, we'll explore another layered function. Stay tuned. Thanks for watching this video. Bye. The function x squared plus 1, all that to the power sine x. I know this looks scary at first glance because the power itself is not a constant, but a function sine x. So when both the base and exponent are functions of x, the best approach is logarithmic differentiation. So what is the first thing we need to do, recalling when the video on logarithmic differentiation? Our first step to do is to apply ln on both sides. This gives us, or this leaves us with, the function ln y equal to ln of the big function x squared plus 1, all that to the sine of x. Now applying our log laws, this gives us ln of y equal to sine of x times ln of x squared plus 1. So what's the next thing to do? Next step to do is to apply the base e on both sides. That is e to the ln of y equal to e to sine of x times ln of x squared plus 1. This, and if we recall very well from our log laws, we note that the derivative or the exponent to the ln of e of x gives us x. In general terms, e to the log here, e to the log of a b gives us b. In this our case, we have e to the ln of y, which is same thing as e to the log to the base e of y, and this gives us y. So this term can boil down to y, and this equals e to the sine of x ln of f squared x squared plus 1. So the first thing we're going to do is let our function f of x be equal to sine x ln of x squared plus 1. This implies that our function y is equal to exponent of another function f of x. Now let's recall our general expression for differentiating functions of this type. From our memory, we know that the derivative with respect to x of a function e to the g of x is same thing as g prime of x e to the g of x. So this calls on, or it tells us to differentiate the function g of x. So what does this imply? This implies then that the derivative with respect to x of our function e to the f of x, which is same thing as the derivative with respect to x of our function e of sine x dot ln x squared plus 1, is going to be equal to f prime of x e to the f of x, or sine x dot ln x squared plus 1, all that prime e to the same function. So it's the same thing that I just wanted to write here. It makes no difference. So let's start with finding first of all our f prime of x. When we look at the function f of x, which is the function sine x dot ln of x squared plus 1, what is the first thing we notice? We first of all notice that this function f of x is the product of two other functions, with our first function being sine x and our second function being the logarithmic function ln of x squared plus 1. So what does this tell us? This tells us that in order to differentiate this function f of x, we will need to call or to apply the product rule. So first thing we then need to do is recall this product rule. What does this product rule state? What does this product rule ask us to do? So let's recall the product rule. Our product rule states that the derivative with respect to x of two functions u times v is same thing as u dv, or u times the derivative of v plus v times the derivative of u. So first of all, what is our u and what is our v in our case of f of x? So in order to do this, we then start with our letics. Our first step to do is to let the function u be our first function, sine of x, and v be our second function, ln of x squared plus 1. Our next step to do now is to find u prime and to find v prime. Let's start with u prime. What does u prime ask us to do? U prime is the derivative with respect to x of our function u, which is the derivative with respect to x of the function sine x. And recalling very well from the video on the derivative of trigonometric identities or trigonometric entities or trigonometric functions, it was well stated and well proven that the derivative of the function sine x gives us the trigonometric function cos x. So we can then conclude that the derivative of u, that is u prime, is our function cos x. Now let's move on to v prime. V prime, which is the derivative of our function ln of x squared plus 1. What does this tell us to do? If we can still recall very well from the video on the derivative of logarithmic principles of logarithmic functions, it was well stated that the derivative with respect to x of the function ln is ln of g of x gives us the function g prime of x on g of x. So this tells us that in order to find this derivative, we first need to find our subderivative g prime of x. So identifying ourselves then with this function, we first need to identify our g of x before we can even start. So let g of x be equal to the function x squared plus 1. This implies that v is same thing as the function ln of g of x, and implies that v prime is then the function g prime of x on g of x. G prime of x, which is the derivative with respect to x of our g of x, which is x squared plus 1, is same thing as the derivative with respect to x of the function x squared plus the derivative with respect to x of the function 1. And this is a perfect application of our sum rule, which states that the derivative of a sum is same thing as the sum of their derivatives. Now let's move on to simplifying this. The first time, the derivative with respect to x of x squared gives us 2x to the 2 minus 1, leaving us with 0. All this gives us 2x plus, what's the next term? The derivative with respect to 1, which gives us 0. And why does this give us 0? Because it was well stated in the constant rule that the derivative of any constant gives us 0. So this then implies that g prime of x is the function 2x. Now, substituting this term back here in order to calculate our v prime, we obtain the function v prime equal to g prime of x, 2x, on g of x, x squared plus 1. So now we have our u prime, we have our v prime, we have our u, we have our v. We can then substitute each and every of this term in our function, in the function u v prime plus v u prime this times. So let's start. Derivative with respect to x of our function uv is u times v prime. What is our u? Our u is the function sine of x times the function v prime, 2x on x squared plus 1, plus v. What is our function v? Which is the ln of x squared plus 1, ln of x squared plus 1, times our function u prime. And what is u prime? U prime is the function, yes, the function cos x. So simplifying this, we have 2x sine x on x squared plus 1 plus ln of x squared plus 1 cos of x. So first of all, what is the derivative of uv? The derivative of uv initially is our function f of x, right? So this derivative is same thing as the derivative of f of x, and f of x is just this term. So what does that tell us? If you can recall very well from our exponent, we were able to simplify all of this to y being equal to the exponent of this, and we said, or recalling from our general laws, that the derivative with respect to x of any function of this form gives us g prime of x e of x. So in order to apply this law, we first need to identify our own g of x. So from our question, we had the derivative with respect to x of the function e to the f of x, and this was supposed to give us f prime of x e of x. Now this f prime of x was noted to be the product of two different functions, x sine x and ln of x squared, and this derivative or f prime of x is what we have just found. So in order to calculate the initial derivative for our function y, we then need to substitute the function f prime of x into this initial function. So substituting that, we then have implies the derivative with respect to x of e to the f of x. This implies that f prime of x, which is equal to f prime of x e to the f of x, gives us 2x sine x divided by x squared plus 1 plus ln of x squared plus 1 cos of x, all that times e to our initial function sine of x ln of x squared plus 1. So we can then conclude that therefore the derivative with respect to x of our function y, which is same thing as the derivative with respect to x of our initial function what's the initial function? Yes, of our initial function x squared plus 1 all that to the sine x, which was same thing as the derivative with respect to x of the function e to the sine of x ln of x squared plus 1. This simplifies to the function 2x sine x divided by x squared plus 1 plus ln of x squared plus 1 cos x times e to the sine of x ln of x squared plus 1. We then enclose our differential. So this is a classic example of how logarithmic differentiation saves us from messy calculations. We combine logs, chain rule, and even implicit. We could combine implicit differentiation, but we have not yet covered that, so we left it out and simplified using logarithmic laws and applications before applying our chain rules and product rules in order to simplify and solve the problem. So in the next question, we'll try solving even more layered and much more complex questions. Thank you and see you in the next video. Bye. Question, we are going to see how all the rules of studied so far, quotient rule, product rule, chain rule, trigonometric, exponential, and logarithmic differentiations can be combined into one tough looking expression. Let's dive right in. First of all, what does this question ask us to do? It tells us to differentiate the function y equal to tan x times e to the power ln of x squared plus 1 all divided by x. At first glance, this looks terrifying, but step by step, we'll break it down. So what's the first thing we have to do? Notice that the numerator has the tan function and an exponential function with a log inside. Then the whole thing is divided by x. So firstly, we're going to simplify this equation. Let's not say simplify, but partition this equation. Let's start with our numerator. Our numerator, first of all, we notice that this function can be expressed as a numerator divided by denominator, which tells us that it can be expressed as a rational function. Hence, we will have to use the quotient rule. So in the quotient rule, what's our first step? We identify our numerator followed by our denominator. So let's start with our numerator. We will say let f of x equal to our numerator tan x e to the ln of x squared plus 1. And g of x, our denominator, be equal to x. So what does the quotient do? Let's recall. It states that the derivative with respect to x of any rational function of the form f of x on g of x is equal to bottom d top minus top d bottom all over bottom squared. We'll call this our equation 1. Yes, I decided let's start labeling our equations to facilitate the solving of the equations and to ensure cohesion between the solutions, throughout the solutions, sorry. So that's our first equation. In this equation, we notice that we're having several terms. We have f prime of x, g prime of x, and g of x all that square, which we don't yet have. So let's start with the first term, f. Let's start with g prime of x. Why g prime of x? Because g of x is simpler. Yes, so let's just start with it, since f of x is going to take us a lot of time to differentiate due to its complexity. So g prime of x, which is equal to the derivative with respect to x of g of x, which is the derivative with respect to x of x, is the function 1x to the power 1 minus 1, which gives us 1. We call this 2. Let's move on to so we're going to move on to our next function, g of x squared. So g of x all that squared is equal to, what is g of x? X all that squared, which gives us x squared. Equation 3. Now let's calculate this term. Since we have g prime of x and we have f of x, let's calculate this term. F of x times g prime of x is equal to, what is f of x? Tan of x e to the ln of x squared plus 1 times g prime of x, 1, which gives us tan of x e to the ln of x squared plus 1, the same function. We'll call this equation 4. So if you notice, we have already calculated our first term and our second term. All it's remaining us is this term. But in order to calculate this term, we first need to calculate f prime of x. So let's work it out. Let's calculate f prime of x. So first of all, let's recall what f of x is. F of x is the function tan x e to the ln of x squared plus 1. So what's the first thing we can notice here? F of x is the product of two functions. One function, which is trigonometric function tan x, and our second function, which is an exponential function with a logarithmic function integrated in it, e to the power ln of x squared plus 1. So first of all, we notice that f of x is the product of two functions. And when we notice that a function can be expressed as the product of two functions, the first formula or the first law or the first rule that comes to our mind is the product rule of differentiation. So first of all, let's recall this product rule. What does this product rule state? The product rule states that the derivative with respect to x of two functions u and v is equal to u dv plus v du. So first thing, what is our u and what is our v? So we will let u be equal to the function tan x and v be equal to the function e of ln of x squared plus 1. Now let's start with our derivative of u. Du on dx, which is equal to u prime, is equal to d on dx of tan x. And recalling from our derivative of trigonometric functions where we worked out, we proved the derivative of tan x with respect to x. If we can recall well, we notice that this gave us the trigonometric function sec squared x. So I've calculated u prime. Let's move to v prime. So first of all, what is v? V is the function e to the power ln of x squared plus 1. Let's recall, when we're still working on the derivative of exponential functions, it was well stated it was well stated that the derivative with respect to x of any function of the form e to the power g of x is equal to g prime of x e to the g of x. So what is our g of x in this case? This box was too big. I just want to reduce the size of the box. So what is our g of x in this case? Our g of x is this function. So let's not call it g of x, since we already have g of x here. Let's use h of x in this case. Let's just wipe it out and write it down fast. H of x is equal to h prime of x e to the h of x. Yes, we changed it to h of x to ensure coherence. We cannot use g of x on top here and then we use again g of x. People might not understand, or it might make the solution a bit blurry. That is less comprehensive. So let's use h of x. So first of all, what is our h of x? Let h of x be equal to ln of x squared plus 1. Now, we still recall very well when working with the derivative of logarithmic functions. It was well stated that the derivative with respect to x of a function ln of, what should we use this time? Let's use n of x is equal to n prime of x on n of x. Sorry if there are many recalls. Yes, it's just that the function is a little bit complex, but I'm sure it's at least coherent enough and well enlisted for easy comprehension. So let's work with this. What is our n of x? We all know. Let n of x be the function x squared plus 1. This implies that n prime of x, which is the derivative with respect to x of the function x squared plus 1, is equal to the derivative with respect to x of the function x squared plus the derivative with respect to x of the function 1, which gives us 2x plus 0, recalling power rule and the constant rule. Power rule, which is the derivative of x to the power 2, is 2x to the power 2 minus 1. Constant rule, which states that the derivative of any constant gives us 0. So this then implies that the derivative with respect to x of h of x, which is h prime of x, is equal to derivative n prime of x on n of x, right? What is n prime of x? 2x on n of x, x squared plus 1. Perfect. But if you can still recall, we calculated h prime of x in order to calculate v prime. Why? Right? We notice that v was equal to e to the power h of x, implies that v prime is equal to h prime of x e to the h of x. This implies that v prime is equal to, what is our h prime? 2x on x squared plus 1 times e to the ln of x squared plus 1. So we have calculated v prime, we have calculated u prime, we know u, we know v. We can then find f prime of x. Hope is comprehensive enough. Sorry. So let's calculate then. f of x was a function u times v. So f prime of x was a function u dv plus v du. So f prime of x is the function u dv plus v du, which give us, let's start with u. What is our u? Our u is the function tan x. What is our v prime? V prime is the function 2x on x squared plus 1 e to the ln of x squared plus 1 plus, what is our v then? Our v is the function e to the ln of x squared plus 1, e to the ln of x squared plus 1. And what is our u prime? Our u prime is the function sec squared x. So let's simplify this. We have our expression, but we need to simplify it. It looks a bit complicated, a bit complex. So we're having two terms in this equation. What is common in both terms? The first thing we can identify as common is the expression. E is the term e to the power ln of x squared plus 1. So we can factorize that out. E to the power ln of x squared plus 1 In bracket, what is remaining? We have 2x tan x on x squared plus 1 plus sec squared x. So I found f prime of x. But recall, let's write it down again, much more clear. X e to the power ln of x squared plus 1 in braces 2x tan x divided by x squared plus 1 plus sec squared x. We can call this equation equation 5. So we then move on to previous equations. Why were we looking for f of prime of x? We were finding f prime of x in order to calculate the term g of x times f prime of x. So now that we have our f prime of x, let us calculate the term g of x, f prime of x. But first of all, what is g of x? If you can recall, this is it above here. G of x is the term x. So g of x, f prime of x gives us x e to the ln of x squared plus 1 braces 2x tan x on x squared plus 1 plus sec squared x. Equation 6. So if you notice now we have our first term g of x, f prime of x, which is our equation 6. We have our second term f of x, g prime of x, which is our equation 4. We have our third term g of x order squared, which is our equation 3. So in order to calculate the derivative of our function, of our complete function y, which is this first term minus this second term divided by this third term, we just substitute it perfectly. So let's move on. Let's substitute dy on the x is equal to our first term x e to the ln of x squared plus 1 in braces 2x tan x on x squared plus 1 plus sec squared x minus our next term, which was f of x g prime of x. F of x g prime of x was this term tan x e to the ln of x squared plus 1 minus tan x e to the ln of x squared plus 1 all divided by g squared. And what is g squared? G squared is x squared. The next thing we do is simplify, noticing that e to the ln of x squared plus 1 is common on both terms. We can factorize it out. E to the ln of x squared plus 1, right? In braces, this x enters, this x multiplied by both terms. We have 2x squared tan x on x squared plus 1 plus x sec squared x minus tan x all divided by x squared. Now we can then perform our common denominator on all of this, or simplify all of this. This leaves us with e to the ln of x squared plus 1 in braces 2x squared tan x on x squared plus 1 minus x sec. Sorry, this is plus. I'm the one that made a mistake. This was supposed to be an underline or something. I went and put it and it confused me. Sorry about that. X squared plus 1 divided by x squared plus 1. If you notice, I'm trying to make all of their denominators to be the same. So if I add this denominator in this term, I need to add it again in the numerator in order to avoid a complete change in the expression. Minus tan x squared plus 1 squared plus 1 divided by x. This then simplifies to e ln x squared plus 1 in braces 2x squared tan x plus x squared plus 1 sec squared x minus x squared plus 1 tan x all divided by x first of all, and x squared plus 1. This x comes from this term here. So that's why it's the way it is. So moving on, let's still simplify. Notice that this can still be simplified. We're still having two terms here which can be simplified. Our first term here is in terms of tan x, and our second term is still in terms of tan x. That means we can factorize tan x out for both terms. This leaves us with e to the ln of x squared plus 1 in bracket tan x was remaining 2x squared minus x squared minus 1 plus we can send this x, we can send this x here into the bracket, leaving us with x cubed plus x sec squared x divided by x into x squared plus 1. So let's simplify this bracket. This leaves us with e to the ln of x squared plus 1 in bracket tan x 2x minus x squared as x squared minus 1 plus x cubed plus x sec squared x divided by x squared plus 1. So we can then conclude that therefore the derivative with respect to x of our function was our initial function. The initial function was tan x e to the ln of x squared plus 1 divided by x, which is equal to dy on the x Okay, so now that our differential is done, I'm just going to highlight something we would have done in the beginning of this question, which I never did. Not because I never wanted to do it, but just if we had done it, it would have simplified the question. And yes, it would have simplified the question. I just wanted a much more complex question for us to walk throughout and enable a better comprehension. So if you notice, if you can still recall your logarithmic laws, you know that e, or let's use a general term, a to the log of a, b is equal to b. This tells you that e is the ln of x squared plus 1, which is same thing as e to the log to the base e of x squared plus 1 is equal to x squared plus 1. So imagine we did this simplification in the beginning. What would we have had? We would have had our y being equal to tan x times x squared plus 1. Now the question looks much more simple. It looks a lot more simple. We would have done it simpler and simpler and simpler. But the aim of this exercise is to enable understanding, not simplicity. When you are working, imagine, like, let me, for example, if this was an exam, it would be better for you to apply this simplification from the beginning. But this is not an exam. This is just an example which was made in order to emphasize the understanding of the concepts. Yeah, so the much more complex or the much more concepts that the example entails, the better it is for an example. So that is why I didn't use this substitution in the beginning. I know that there are lots of you guys who are wondering why we didn't simplify it from the beginning. So here's the reason. So let's just apply this simplification to our final answer here. We have dy on the x being equal to x squared plus 1 into x squared minus 1 tan x plus x cubed plus 3 into sec squared x all divided by x squared plus 1, leaving us with This cancels this. X squared minus 1 on x than x plus x into x cubed, x squared, sorry, plus 1 sec squared x on x. X cancels out. We are leaving us with x squared minus 1 on x than x plus x squared plus 1 sec squared x. So we could still conclude that the derivative with respect to y, with derivative of y with respect to x leaves us with x squared minus 1 on x, all that tan of x plus x squared plus 1 sec squared x. So this is a much more simpler form we would have had, or we have still gotten, using this simplification. Okay, so sorry, there was an error. I was just going through the solutions and I noticed that an x squared here turned to x out of a sudden, all of a sudden. Wow. Well, sorry for that error. Let's just correct it quickly. Yes, squared. We have squared. We have squared. We have, yes, normal there. We have squared. We have squared. We have squared. Squared. We have squared. We have on x still here. Squared on x. And this can be simplified to 1 minus 1 on x squared than x plus 1 plus 1 on x plus x plus 1 on x sec squared x. Wow, so thanks a lot. I'm sure there aren't any more errors in the question, but thanks a lot, and here is the solution to this question. Okay, so now, just for a test, let's try and simplify the equation from the beginning and then solve it throughout. So given that we simplify the equation from the beginning, what would we have had? We would have had y equal to x squared plus 1 than x divided by x. So let's solve this question. Let's solve it. So first of all, this can still be seen as a quotient, that is with a numerator and a denominator, and it can still be seen as a product with our first term and our second term. Let f of x be equal to our first term x plus 1 on x implies that f prime of x, which is bottom the top minus top the bottom on bottom squared. This leaves us with x. What's the differentiation of x squared plus 1? We have 2x plus 0 minus x squared plus 1. Differentiation of x, 1 divided by x squared, leaving us with 2x squared minus x squared minus 1 on x squared, leaving us with x squared minus 1 on x squared, which gives us 1 minus 1 on x squared. So let's then calculate. Let g of x be equal to tan x implies that g prime of x is equal to sec squared x. This then implies that y prime, which is dy on the x, which is equal to f of x, f times g prime was f squared plus 1 on x times g prime of x plus g times f prime of x. What is our g? Tan x times f prime of x. And this still simplifies to 1 minus x squared than x plus x squared sec squared x. And this gives us same answer as we have above. So what does it tell us? It tells us that no matter the case, that is whether we simplify or we don't simplify, we come out to the same solution. But without simplification, the work is much more messy, much more complicated, and much more hard to calculate. Whereas with a good and simple simplification, the work or the solution can be summarized to just a couple of lines. So just to advise you guys, when you're having a solution or when you're having a question, the first thing you do is check if that question or that differentiation can be simplified from the beginning. If yes, simplify before differentiating. So in conclusion, in this question, we combine the trigonometric, exponential, logarithmic, product, quotients. We didn't use chain. Yes, we use constant rule, constant multiplier rules. We use a lot of the differentiation rules in order to solve this question. So in the next problem, we'll go even deeper with a power raised to a power type of function. So thank you. I'm waiting for you guys in the next video. Bye. So in this question, we are going to use the notions on implicit differentiation which we studied in our previous video in order to solve or to differentiate this question below, that is to find the y and the x. So first of all, let's recall the different steps we enlisted in order to use implicit differentiation to find the y on the x. What was our first step? Our first step was to ensure we have an equation in terms of x and y. And observing this question, we already see or we already know that this question is an equation in terms of x and y. Moving on to our second step. What did the second step ask us to do? It asks us to apply or to derive both sides, to apply the differentiation or the derivative with respect to x on both sides of the equation, that is the left hand side and the right hand side. So let's apply it. D on the x of our left hand side, sine of xy plus x squared y equal to d on the x of y cubed plus cos of x. So opening the bracket, we have d on the x of sine xy plus d on the x of x squared y equal to d on the x of y cubed plus d on the x of cos x. So in this question, we observe that there are four different terms in which we need to apply the differentiation, or four different terms to differentiate. Our first term being sine of xy, second term x squared y, third term y cubed, and fourth term cos x. So we're going to take term by term and apply differentiation. So let's start with our first term, sine of xy. So when we observe this, what do we note? The first thing we notice is that this is a function of a function, with our first function xy and our second function the sine function. And every time we have a question or an equation which is a function of another function, the first rule or the first thing that comes to our mind is to use the chain rule. So first of all, what does the chain rule state? Let's recall the chain rule. It says that the derivative with respect to x of a function in terms of another function, that is f of g of x, is going to be equal to f prime of g of x times g prime of x. So the first thing we need to do in this case is to identify our g of x and our f of x. So we'll say let g, we'll not say let g of x, we'll just say let g be the function. Why do we say g? Because g of x is a function in terms of x, whereas our function in this case is a function in terms of x and y. So we could still say let g of x comma y be equal to xy. This implies and let f of u be equal to sine u. So we're going to start first of all by finding f prime of u. F prime of u then is equal to the derivative with respect to u of the function sine u, which gives us, recalling the video on the derivative of trigonometric functions, it was well proven and well stated that the derivative of our function sine x, or sine u in this case, is equal to cos u. So moving on to our next term, that is substituting let u, not letting u equal to g of x then implies that f prime of u, which is equal to f prime of g of x, is the function cos of g of x, which is cos of xy. So we are not yet done with our complete differentiation. We have found our first term f prime of g of x. We still need to find our second term g prime of x. So g of x is the function xy, and what we notice is that g of x is a function which is represented by the product of two different functions, with our first function being x and our second function being y. And every time we have a function which is the product of two other functions, the first rule which comes to our mind is the product rule. So what does the product rule state again? Let's recall the formula. The product rule states that the derivative with respect to x of a function uv is equal to u dv plus v du. So in this case, we then need to identify our u and our v. Let u be equal to x. It implies that u prime, which is the derivative with respect to x of u, which is the derivative with respect to x of x, gives us the function 1. Let v be equal to y. This implies that v prime, which is the derivative with respect to x of y, is equal to the derivative with respect to y, derivative dy on the x, times derivative of y with respect to x, with respect to y, with respect to y. This formula was well stated in the previous video when we were working on derivative of implicit functions. It was well stated that the derivative with respect to x of a function f of y is equal to dy on the x times the derivative of that function with respect to y. So in this case, our function f of y is the function y. So the derivative with respect to x of y gives us dy on the x times d of our function y with respect to y, which gives us dy on the x times 1. So we can then conclude that g prime of x, which is u dv, what is u? X times dv is dy on the x, plus rv y times du, which is 1. So this gives us x dy on the x plus y. So we have calculated our g prime of x and we have calculated our f prime of g of x. So we can then calculate the derivative for our first term, which is f prime of g of x times the g prime of x. So the derivative with respect to x then of our first term, sine of xy, gives us cos of xy, that is f prime of g of x times g prime of x dy on the x plus y. Let's open our braces, leaving us with x dy on the x cos of xy plus y cos of xy. So in conclusion, for our first term, the derivative with respect to x of the function sine of xy gives us x dy on the x times the cos of xy plus y cos of xy. So this is our first equation. So we are done with deriving our first term. We are done with this derivative. So let's move on to our second derivative, the differential with respect to x of the term x squared y. The derivative with respect to x of the term x squared y. So this is our next term. The first thing we identify is that this function x squared y is still the product of two functions, with our first function being x squared and our second function being y. Knowing that it is a product of two functions This automatically tells us that in order to perform this differentiation, we will need to use or to apply the product rule. What does the product rule state? The product rule statement has been recalled here above, so we'll just use the same formula. So in order to do this, we first need to identify our u and our v. So we'll say let u be the function x squared. This implies that the derivative of u, or u prime, let me just write it directly. This implies that u prime is equal to the derivative with respect to x of our function x squared, which from our power rule gives us 2x. Now we let v be the function y. This implies that v prime is equal to the derivative of y with respect to x, which gives us dy on dx. This then implies that the derivative with respect to x of our function x squared y is u dv plus v du. What is our u? X squared times dv dy on dx plus v y times du 2x, leaving us with x squared dy on dx plus 2x. So we can then conclude that the derivative of our second term, x squared, or our second term, sorry, gives us x squared dy on dx plus 2xy. We call this equation 2. Let's move on to our third term. What does our third term ask us to find? In our third term, we are asked to derive with respect to x the term y to the power 3 or y cubed. So let's work on that. The derivative with respect to x of our function y cubed is equal to the derivative of y with respect to x times the derivative of our function, which is in terms of y with respect to y. This is just an application of this formula, which was well stated and well explained in the previous video. So let's move directly to finding this term. This gives us dy on dx times the derivative of y cubed with respect to y. We can directly apply the power rule, which gives us 3y to the 3 minus 1, which gives us 3y squared dy on dx. We can then conclude that the derivative with respect to x of our term y cubed gives us 3y squared dy on dx. We label this equation 3. Let's move on to the fourth term of our equation. This fourth term tells us to differentiate the function cos x. Recalling the derivative of trigonometric functions, we notice that, or we recall that the derivative with respect to x of the function cos x gives us negative sine x. We call this our equation 4. So we have calculated, or we have already determined our 4 different terms. So all what is remaining for us to do is to substitute these different terms in our general equation. That is our first term plus our second term equal to our third term plus our fourth term. So let's do that. What's our first term? Our first term is x dy on the x cos xy, x dy on the x cos xy plus y cos xy plus y plus y. Let me check. Yes, plus y cos xy is okay. Plus y cos xy plus our second term, which is x squared dy on the x plus 2xy, x squared dy on the x plus 2xy equal to our third term, which is 3y squared dy on the x plus our fourth term, which is minus sine x. So after completing this step, our next step then is to use algebraic methods or algebraic identities and algebraic methods in general to make dy on the x, or to find dy on the x. The first thing we need to do in this case is make dy on the x the subject of the formula. How do we make dy on the x the subject of the formula? This can be done by moving all terms which contain dy on the x to one side. So let's move it to our left hand side. Our first term is x dy on the x cos xy. This term contains, so we'll leave it on this side, x squared dy on the x. So we're done with this term. We're done with this term. This term also contains, moving it to the opposite side, turns to a minus y squared dy on the x. Those are all the terms which contain dy on the x. Now we move all the terms without dy on the x to the other side. We start with this term, negative y cos xy. The next term, minus 2xy. The last term, minus sine x. We can then factorize dy on the x, leaving us with x cos xy plus x squared minus 3y squared equal to minus, let's factorize minus out, y cos xy plus 2xy plus sine x. This leaves us with dy on the x being equal to minus in bracket y cos xy plus 2xy plus sine x, or divided by x cos xy plus x squared minus 3y squared. So we can then conclude, therefore, the derivative of y with respect to x, that is dy on the x, gives us the function negative in bracket y cos xy plus 2xy plus sine x bracket close, all divided by x cos xy plus x squared minus 3y squared. We box or we enclose our answers. So in this question, although the question it looked a bit complicated from the beginning, using our steps which we established in the previous video on the differentiation of implicit functions, we're able to carefully differentiate this function, that is implicitly differentiate each term. After differentiating each term, we're able to make dy on the x the subject of the formula in order to find dy on the x. So after finding this, we're left with dy on the x being the function negative in bracket, we have y cos xy plus 2xy plus sine x bracket close, all divided by x cos xy plus x squared plus, is this plus? Yes, minus 3y squared. So thank you for watching this video. See you in the next video. Bye. So in this question, we are still going to use the knowledge of implicit differentiation which we applied in the previous example and the initial video on implicit differentiation in order to solve this question below. So first of all, what does this question ask us to find? This question asks us to find dy on the x, given that e to the xy plus ln of y equals x squared minus y squared. So in order to find dy on the x, we need to recall the steps we enlisted in the first video on the differentiation of implicit functions. So what was our first step? The first step asks us to first of all see or observe if we have a function in terms of x and y. Observing our function, we notice that this function is already a function in terms of x and y, so the first step is already completed. So what does the second step ask us to do? The second step asks us to apply differentiation with respect to x on both sides of the equation. So let's work on that. Applying on both sides, we have derivative with respect to x of e to the xy plus ln of y equals to the derivative with respect to x of x squared minus y squared. Opening the brackets, that is using our sum and difference rules of differentiation, which tells us that the derivative of a sum or the derivative of a difference is equal to the sum of their derivatives or the difference of their derivatives. So this leaves us with derivative with respect to x, or d on the x, of e to the xy plus d on the x of ln y equal to d on the x of x squared minus d on the x of y squared. So in this question, we still have 4 terms just like the previous example. So we are going to tackle this step by step, taking term by term, explaining carefully in order to find the solution of these terms or to find their differentials. So let's start with our first term. Derivative with respect to x of e to the xy. So the first thing we observe is that this is an exponential function, and not just any exponential function, but in this case the power is not just x, it is a function in terms of x and y, or it's a function on its own. So let's recall our formula when we were working on exponential differentiations, which said that the derivative with respect to x of the function e to the power g of x is equal to g prime of x times e to the power g of x. So first of all, in this our case, what is our g? Let's first of all identify our g. So we are going to let g of x y, not just g of x, because in this our case, g is a function in terms of x and y. So let g of xy be the function x times y. So we then need to calculate g prime of x. G prime then, which first of all, in order to calculate g prime, the first thing we observe is that this is a function, is the product of two functions. So in order to find its differentiation, we need to use the product rule. So what does this product rule state? It says that the derivative with respect to x of a function, let's say u v, is equal to u dv plus v du. So what is our u and what is our v? So let u then be equal to x, implies that u bar, u prime, which is the derivative with respect to x of x, gives us 1. Now we are going to let our v be the function y. This implies that v prime, which is the derivative with respect to x of y, gives us dy on the x times the derivative of y with respect to y, which gives us dy on the x times 1, hence dy on the x. So what does that tell us? That tells us then that g prime is the function u dv x times dy on the x plus v du, leaving us with x dy on the x plus y. So we can then conclude that the derivative with respect to x of our function e to the xy leaves us with g prime of x, which is x dy on the x plus y times x times e to the xy. Opening the bracket, we have x dy on the x e to the xy plus y e to the xy. We can then conclude that the derivative with respect to x of our first term xy leaves us with x dy on the x e to the xy plus y e to the xy. We call this equation 1. So let's move on to our second term. What does our second term ask us to find? Our second term asks us to differentiate ln of y. So let's work on that. Derivative with respect to x of ln of y. Recalling, first of all, in order to calculate it, this is the same thing as the derivative of y with respect to x times the derivative of ln of y with respect to y. And if we recall our formula, or in the case of derivative of logarithmic functions, it was well stated that the derivative with respect to x of a function ln x is equal to, it was well proven, not just stated, is equal to 1 on x. So this gives us dy on the x times 1 on x. So we can still conclude that the derivative with respect to x of our term ln y is 1 on x times dy on the x. We are going to label this equation 2. So let's move on to our third equation. What does it ask us to do? Our third term, the derivative with respect to x of x squared. That one is simple since it's not in terms of y. Derivative with respect to x of x squared, applying direct power rule, gives us 2x. Our third term, let's move on to our fourth term, which tells us to differentiate with respect to x, the term y squared. So the derivative with respect to x of y squared is equal to the derivative with respect to x, dy on the x, times the derivative of y squared with respect to y. And this gives us the derivative of y with respect to x times the derivative of y squared with respect to y. Directly applying the power rule leaves us with 2y. So this then implies that the derivative with respect to x of our term y squared gives us 2y dy on dx. We call this our fourth term. So after calculating these four different terms, the next step we need to do is directly substituting each and every one of these terms in our general equation. That is, our first term plus our second term equals our third term minus our fourth term. So let's work this out. What's our first term? Our first term is x dy on the x e to the xy, x dy on the x e to the xy plus y e to the xy plus y e to the xy plus our second term, which is 1 on x dy on the x, equals our third term, which is 2x, minus our fourth term, which is 2y dy on dx. So the next step in this solution is to use algebraic principles in order to find dy on the x. But how do we use algebraic principles in order to find dy on the x? The first thing we need to do is isolate all the terms with dy on the x on one side. That is, moving the terms which contain dy on the x to the left hand side in our case. So our first term with dy on the x is the term x dy on the x e to the xy. What's our next term? Plus 1 on x dy on dx. Our third term, which is this, moving it to the other side, the negative becomes a positive sign, leaving us with 2y dy on dx equal to, we have our first term here which is not in terms of y, we move it to the other side, negative y e to the xy equal to our last term which is already on the other side, plus 2x. So having done this, we can then factorize out dy on the x on all the terms of our left hand side, leaving us with dy on the x equal to, in brackets, x e to the xy plus 1 on x plus 2y, all that equal to 2x minus y e to the xy. So in order then to calculate our dy on the x, all we need to do is divide both sides by this term, leaving us with dy on the x being equal to the term 2x minus y e to the xy, all that divided by x e to the xy plus 1 on x plus 2y. So we can then conclude that is therefore the derivative of y with respect to x in our case gives us the equation or the expression 2x minus y e to the xy divided by x e to the xy plus e to the xy plus 1 on x plus 2y. We enclose or box our answers. So thank you for being with us throughout this video. Hope you guys have understood perfectly the solution. To find dy on the x, given that tan xy plus e to the y equals x cubed plus y ln x. So the first thing we need to do in this case is to recall the different steps or procedures we need to follow in order to apply implicit differentiation on this question. So what was our first step? Our first step was to first of all determine or to analyze if we already have a function in terms of y and x. So in this case, we already have a function in terms of y and x, as it is evidence in the case that we have terms in terms of y and x. For example, tan xy, which is a function in terms of x and y in x, which is a function in terms of y and x. We have x cubed here, which is a function in terms of x, e to the y, which is a function in terms of y, all of that mixed in the same equation. This already tells us that we have a function in terms of x and y. So what's the next step? The next step is to apply differentiation with respect to x on both sides of the equation. So let's work that out. This leaves us with d on the x of tan xy plus e to the y equals the d on the x of x squared, x cubed, sorry, plus y ln x. Opening the bracket, we have d on the x of tan xy plus d on the x of e to the y equal to d on the x of x cubed plus d on the x of y ln x. So let's start this step by step, just like previous example, taking term by term. So let's start with our first term, d on the x of tan xy. So what's the first thing we notice? The first thing we observe is that this is a function of another function, with our inner function being xy and our outer function being the tan function. And this already tells us that in order to differentiate this, we need to use the chain rule. But what does the chain rule tells us? The chain rule tells us that if you have a function that is a derivative with respect to x of a function f of g of x, this is same thing as f prime of g of x times g prime of x. So the first thing we're going to do is let u be our inner function x, y. This implies that our outer function can be written as, or f of u can be written as tan of u, implying that f prime of u, which is the derivative of u, is the function derivative with respect to u, in this case, yes, of tan of u. And recording from our differentiation of trig function, the derivative for the function tan x, or tan u in this case, is sec squared u. So this then implies that f prime of u, which is f prime of xy, is equal to sec squared of xy. So let's then move on to our g prime of x. Now we let still u be equal to g prime of x, or we could directly say u prime. This implies that u prime, which is equal to g prime, is equal to the derivative with respect to x of our function xy. When we look at this function, we notice that this is still a product of a product, right? The product of two different functions, sorry. And when we have the derivative of any function which can be written as a product of two different functions, with our first being x and our next being y, the first thing we have to recall is that in order to calculate this, we need to use the product rule. And what does this product rule state? It states that the derivative with respect to x of two functions multiplied by each other, uv, gives us u dv plus v du. So first of all, what's our u, what's our v? We let, or what we already use here, let's just let small u, yes, or we use a and b in our case. Let a be the function x, implies that a prime is equal to 1, and let b be the function y, implies that y b prime is equal to dy on dx. This implies that g prime is equal to u dv x dy on dx plus y times 1, which gives us x dy on dx plus y. So we can then conclude that our function this, which is f prime of g of x times g prime of x, that is sec squared of xy times this gives us, that is the derivative with respect to x of tan of xy gives us sec squared xy into x dy on the x plus y. Opening our brackets, we have x sec squared xy dy on the x plus y sec squared xy. So we can then conclude that the derivative with respect to x of the function tan of xy leaves us with x sec squared xy dy on the x plus y sec squared xy. We label this equation 1. So let's move on to our second term. What does our second term ask us to do? It asks us to differentiate the function power y. The derivative with respect to x of the function e to the power y is same thing as the derivative of y with respect to x of the function times, derivative of y with respect to x times the derivative of our function e of y with respect to y. This can all be evident to the formula. The derivative with respect to x, that's the general expression of any function of the form f of y, that's any function with respect to y, or any function dependent on y, is dy on the x times the derivative that our function with respect then to y. So this gives us dy on the x. Now what's the derivative of e of y with respect to y? We call it exponential derivatives. The derivative e to the power x with respect to x still gives us e to the power x. So this tells us that the derivative of e to the power y with respect to y still gives us e to the power y. So we can then conclude, implies that the derivative with respect to x of our term ey gives us e to the power y dy on the x. We label this equation 2. So let's move on to our third term. Our third term in this case asks us to differentiate x cubed. This is very simple and direct. The derivative with respect to x of the function x cubed gives us 3x squared. We label this equation 3. Moving on to equation 4. Moving on to our fourth term, which tells us to derive the function y in x. That is the derivative with respect to x of y in x. So what's the first thing we observe here? We observe that this is still a product of two different functions, with our first function being y and our second function being x. Recalling the same formula above here, the derivative of the product of two different functions can be written as u dv plus v du. So first of all, what's our u and what's our v? We'll let u be the first function y, implies that u prime, which is the derivative of y with respect to x, and this gives us dy on the x. We will also let v be equal to ln x, and this implies that v prime, which is the derivative of ln x with respect to x, and this gives us 1 on x. Responding the video on the derivative of logarithmic functions. It was well stated and well proven that the derivative of ln of x gives us 1 on x. So this implies that the derivative with respect to x of our function y ln x gives us u dv y times 1 on x plus v du. U dv plus v du. Our v being ln of x times du dy on the x. This gives us y on x plus ln of x times dy on the x. So we can then conclude that this implies the derivative with respect to x of our function y ln x gives us y on x plus ln of x dy on dx. We label this equation 4. So we are done with calculating our 4 different terms. What's the next step we need to do? To substitute these 4 different terms or these 4 different solutions in our initial equation. So substituting this will leave us with our first term, that is term 1 plus term 2, equal to the third term plus the fourth term. So let's start. What's our first term? Our first term is x sec squared xy dy on the x with braces x sec squared xy dy on the x plus y sec squared xy. That's our first term, plus our second term being e to the power y dy on the x, e to the power y dy on the x equals, so our third term being 3x squared, 3x squared plus our fourth term y on x plus ln x dy on the x. Let me put this where this doesn't look that much as ln yes, that is it. So in order, after applying this or after calculating our different terms and substituting the general equation, the next thing we need to do then is to use algebraic laws or algebraic principles in order to find one's x. The first step we need to do, or the first thing we need to do, is to move all the terms containing dy on the x on one side of the equation, that is making dy on the x the subject of the formula. So what is our first term? X sec squared xy dy on dx. Our next term plus ey dy on the x. Our last term, which is this, is on the other side, so moving into the other side, to the left hand side, the plus becomes a negative, leaving us with ln x dy on dx equal to our next term. We need to move it to the other side, minus y sec squared xy plus 3x squared plus y on x, that is plus this plus this. Now on our left hand side, we factorize dy on the x out since it's common throughout the three terms, leaving us with dy on the x in bracket x sec squared xy plus e to the power y minus ln x, all that equal to 3x squared plus y on x minus y sec squared x. So this then tells us that dy on the x is the term 3x squared plus y on x minus y sec squared xy, all divided by x sec squared xy plus e to the y minus ln of y. So in conclusion, therefore, the derivative of y with respect to x in this our term, in this our question, gives us the equation or the expression 3x squared plus y on x minus y sec squared xy divided by x sec squared xy plus e to the y minus ln x. We enclose or box our answers. So thank you for being with us throughout this video, throughout this calculation. Hope you guys have understood step by step. If you have any questions, feel free to post them in the comment section below, and I'll do my best to respond to them. So thank you and see you in the next video. Bye.